general theorems without proof. I hope that we will have time to prove Torelli theorem for K3 surface, but not today. Today I will just formulate. Okay, so last time we discussed a general notion of Hodge structure, polarized Hodge structure, and so on. And now let me give some examples. So today we will discuss first, weight 1. Okay, so for weight 1, we have a bijection between complex tori and integral Hodge structures of weight 1. So how does this bijection work? So suppose we have an integral Hodge structure, then we can consider it embedding inside its complexification, and then we can consider its projection to 1, 0. So we obtain in such a way lattice V inside V01, and we say that the corresponding complex torus is this one. Okay. And vice versa, suppose we have a complex torus Cn, and there is a lattice inside it. Then we can consider Cn as a real vector space that is an extension of the lattice with an almost complex structure. Almost complex structure on it. So let me recall that an almost complex structure is an endomorphism of a real vector space such that its square is a minus identity. Okay? And so the corresponding integral Hodge structure is the following. So we consider complexification of this real vector space. Then there is an action of an almost complex structure on it. So we can consider its decomposition into two subspaces of eigenvalues of this. Here we have an almost complex structure that acts here. Then we can consider it the corresponding endomorphisms of a complexified vector space. So what are eigenvalues of this and this subspaces?
Plus minus I.
So this is an eigenvalue I, and this is an eigenvalue minus I. And so in such a way, we obtain an integral Hodge structure of weight 1. And it's easy to see that these two correspondents are inverse to each other. Okay? So there is a bijection between these two.
I thought that when we go from left to right, we obtain algebraic.
No. Here we can to obtain an algebraic abelian variety, we need to consider polarized Hodge structure. I will say this in a minute. But if we just consider integral Hodge structure of weight 1, then we obtain some complex terms. So because here we can obtain any lattice. Okay, so a general bijection is the following. Okay, and now let me formulate what we have for abelian varieties.
So you require the lattice to be a rank 4 here.
No. Here we complex terms of any dimension.
Okay. Yes.
So here we can take just any dimension and obtain in such a way, a complex terms. Okay. And now for abelian varieties. This gives polarizable integral. Polarizable integral Hodge structures of weight 1. Okay, I will not explain why this is so. Today lecture will be just обзорная. Как сказать? Will be a survey lecture. Okay, just some funny facts from algebraic geometry that that I would like to present in this course. Okay, so abelian varieties are in bijection with polarizable integral Hodge structure. So an integral Hodge structure such that there exists a polarization on E. Go sleep. There is a bijection between polarized. So there is a difference between polarizable and polarized. Between polarized abelian varieties and polarized integral Hodge structure. So this means that if we choose a polarization on an abelian variety, then we will obtain polarization on the corresponding integral Hodge structure. And if we if we consider just abelian variety without fixed polarization, then here there exists a polarization on the corresponding Hodge structure. Okay, so this is a geometric picture for weight 1 Hodge structures. Okay, and now let me formulate the first Tarelli theorem. Global Tarelli theorem for curves. So we say that two smooth, compact, complex curves C and C prime are isomorphic if and only if there exists an isomorphism of the corresponding integral Hodge structures on the first cohomologies. Of integral Hodge structures respecting the intersection pairing. So, okay, this is just a statement. We will not prove it. We will try to prove an analogous statement for K3 surfaces later. But now I would just wanted to formulate this theorem because this is a very nice and classical statement. Okay, and now let me discuss Hodge structures of weight 2, and in particular Hodge structures for what we have for K3 surface. So Hodge structures so first lemma. And maybe I will send you exercise maybe next week, maybe on weekends, because I think that maybe for Tori, for complex Hodge structures of weight 2 for abelian surfaces or complex Tori of dimension 2, it's better to leave as an exercise of this. Statements. Now let us discuss what we have for K3 surfaces. For complex K3 surface, yes, Hodge structure on its second homologous is completely determined by 2-1 subspace. And if it is generated by an element sigma, then the self-intersection of sigma is 0, and intersection with its conjugated is greater than 0, where this is an intersection form. We will use this later when we will discuss periods of K3 surfaces. Okay, and now why we have this lemma? We have it just because Hodge decomposition is related with the multiplication in cohomologies. So if we consider multiplications, K1 for any complex variety, K1 plus K2 XC, then It is related with the Hodge decomposition in the following way. Is mapped to what? Here. Do you know?
P1 plus P2,
Mm-hmm.
Q1 plus.
Okay, and now what this gives us in our setting. So we have a K3 surface. Then this is mapped to it first, cohomologous, and here, what is the Hodge decomposition for a K3 surface? Еще засну.
H22 equals.
H22, and we don't have any other components, right? So from this, we see that one component of the corresponding Hodge structure is defined as an orthogonal to 0. Right? Using just this multiplication. And now, since we know that these two subspaces are conjugated to each other, we see that completely determines the whole Hodge structure.
But we also need to fix the scalar product.
Yes, but here we already have an intersection form, right? Because we already have a K3 surface, and we already have this multiplication. We want to figure out just the Hodge structure, just the corresponding decomposition on the complexification of cohomologies. And I claim that it completely determined by 2, 0, by just one vector, because 0, 2 is just conjugated to this vector, and this part 1, 1 is an intersection of its orthogonals. Okay, we have already discussed what is the intersection for on a K3 surface before. This was an E8 lattice with copies of hyperbolic plane. And now we discuss Hodge structures on it. And now, so what we obtain, so I denoted by sigma the corresponding vector, and from this we immediately obtain that the intersection of sigma with itself is 0. Okay? And now for this thing, this intersection is just by definition an integral over this form, and this is a positive form. Do I need to explain why it's positive?
Please, and also please recall how the self-intersection is just zero.
Just because if we consider 0, 0, then we will obtain what's component here? 4, 0, right? And this is 0.
Yeah.
So from this we obtain this thing and also this self-intersection. And now if we consider 2, 0 intersection with 0, 2, then we will obtain something here. And we want to prove that this is something positive. Okay, but this is, I think this is a local computation because so if we have an element here, then it is represented by global holomorphic form omega, and locally this form is holomorphic, some holomorphic form. In local coordinates, this holomorphic form is some holomorphic function z1, dz2, right? Locally we can write it in such a way. Okay, this is just holomorphic function. Then omega conjugated locally is what? This is a conjugated holomorphic form. Okay, and now when we consider this product, we obtain dz1, dz1, dz2. So this is a volume form, and this is something positive. So that's because this is positive. Okay. So okay. This was a statement about Hodge decomposition for K3 surface. And now also let me say that if S is an algebraic K3, then the corresponding Hodge structure is polarizable. Okay, and now let me formulate our goal for the next lectures, global Tarelli theorem for K3 surfaces. So this theorem was proved by how to write this in English? Piasecki-Shapiro. Shapiro. And Shofarevich. Ладно. For an algebraic case. And I...
Shapiro, it's two different people.
No, it's one. It's Piasecki-Shapiro. And Shofarevich is the other one. Okay, I think historically this was the first proof in the algebraic case. Это где-то 70-е, по-моему. Я давно не заглядывала в эту студию. And I think I will follow this classical proof, most probably, for an algebraic case, and then Burns, Rappaport for non-algebraic for all K3 surfaces. Okay, and now the statement. The two K3 surfaces S and S prime are isomorphic. This is over complex numbers. If and only if there exists an isomorphism H2SZ of integral Hodge structure structures respecting an intersection form. Intersection pairing. Okay? So this is a statement. So two K3 surfaces are isomorphic if there exists an isomorphism of the corresponding Hodge structure that respects intersection pairing. Note that here this isomorphism cannot is not always induced from an isomorphism of S and S prime. And to formulate a more precise statement, I need to explain what is the Keller conus. So today I will explain what is this, just to formulate more precise statement, because here I want to underline that this isomorphism does not necessarily comes from an isomorphism between two K3 surfaces.
So if they are isomorphic, there should be an isomorphism.
Yes, if they are isomorphic, then there exists an induced isomorphism. But what I claim is that this isomorphism, it can be just an abstract isomorphism that does not come from an isomorphism of two K3 surfaces. There should be an additional condition for this isomorphism to be induced from the isomorphism of the corresponding K3 surface. Okay, so this is just some abstract isomorphism in this setting. Okay, and but before this, yes, but before this, let me also give some new definitions, because I also want to formulate derived global Tarelli theorem, that is a Tarelli theorem for derived categories. I hope that we will have time in December to discuss it, at least on the level of formulations. Okay, now I want just to formulate it. Everyone knows what is a bound derived category of coherent shapes? Do you know?
I can learn it in November, so.
Okay, then we will discuss this. And do you know?
Yeah.
Okay, we will discuss all this more precisely in December, but now I just, in this survey lecture, I just want to advertise what we will have later. Okay, so to formulate a derived global theorem, I need to define transcendental lattice. So note that, so first of all, note that here it contains two neutral structures. So first substructure we have already discussed. This is what? Last time we discussed this.
Hodge.
Hodge classes. Intersecting this. And this is, in our case, Neron-Siverio group of S, and this is Picard group of S. And the second one is so-called transcendental lattice. Let me define it. This is a lattice here. That is a minimal primitive Hodge substructure. Structure that contains our favorite part of Hodge structure. Moreover, such that its 2-0 part not just contains, it is equal to 2-0 part of S. Okay, so this is a definition of transcendental lattice. Okay, and now let me formulate what is the derived global Torelli theorem. Yes, so in fact, there exist non-isomorphic K3 surfaces with isomorphic transcendental lattice. But this is a very important lattice here, and I want to formulate derived Torelli theorem just to explain why it plays so fundamental role in the theory of K3 surfaces. So theorem derived global Torelli theorem that was proved by Mukai Arlo to complex K3 surfaces as not just algebraic, complex algebraic, here it's important. Algebraic K3 surfaces S and S prime have Hodge isometric transcendental lattices if and only if their derived categories are equivalent. Equivalence of C linear triangulated categories. So let me give some comments here about this statement. First of all, for those who don't know what is bounded derived category of cogherent sheaves. So let me just say now that this is an important invariant of an algebraic variety. This is called bounded derived category of cogherent sheaves. So here we consider an abelian category of cogherent sheaves, and now we can associate to an abelian category so-called triangulated category, so-called derived category. More or less, we inverse quasi-isomorphism. So we we will discuss this more concretely later. Okay, so we have this invariant, and so if we consider just cogherent abelian category of cogherent sheaves, this is in some sense and not very isn't a very interesting invariant of algebraic varieties, just because there is a theorem of Gabriel that tells you that we can that abelian category of covariant shifts completely determines your algebraic variety. And for derived category of covariant shifts, this is not so. There is a statement that was proved by Bondel and Orlov that if your canonical class is ample or anti-ample, then this invariant completely determines your variety. Okay, we can reconstruct an algebraic variety from its bounded derived category of covariant shifts, but not that here canonical bundle is trivial. So we cannot apply, as in fact in abelian case too. So we cannot apply theorem of Bondel and Orlov. And precise statement, so we can't completely reconstruct K3 surface from its bounded derived category. And this statement tells you what we can reconstruct. So in this case, these invariants are isomorphic if and only if the corresponding transcendental lattice are isomorphic. So this part determines your bounded derived category. I'm not sure that we will, in fact, I'm not sure that we will have time to discuss this, but at least I give you the statement, okay? So the statement is the following. So for bounded derived categories, we have this.
So this substructure determines the derived category, and the whole structure determines the whole K3 surface.
The transcendental lattice doesn't. This is an important invariant, but it. So there exist non-isomorphic K3 surfaces with isomorphic transcendental lattice. So there exist non-isomorphic K3 surfaces with isomorphic bounded derived categories of covariant shifts. Okay, so this doesn't determine the whole variety, but this determines your derived category. Okay. Okay. And now, yes. For complex torus, maybe I will leave Hodge structures for complex torus. I will leave as an exercise. And now, let me give. And now I want to discuss something about positive cons for complex K3 surfaces, and then Keller cons. And in the end, I would like to formulate classical Torelli theorem for complex K3 surfaces in the whole generality. Okay, so this was just formulations, and now let me discuss some more concrete things. Everything is clear?
Yes.
Mm-hmm. Okay. I would like first, before discuss Keller con, I would like to discuss ample con. Of course, this is non-empty only for projective K3 surface, but in any case, we can. I would like to give some precise statements about it. So first of all, let me remind something from the first course of linear algebra. So suppose we have a real vector space, dimension n+1, and we have a non-degenerate quadratic form of signature 1n. So as an example, of course, for us, an example will be Picard group of a K3 surface. K3 surface tensored by R with an intersection 4. We have already discussed that this has signature 1n. Okay. Then there is a con of vectors in V with positive self-intersection. Then this cone has two components. Yes, so this is an interior, so there is a, so we can choose coordinates in such a way that our quadratic form can be written in such a way. This is the corresponding quadratic that is a singular cone, and these two components is just interiors of this cone, right? Okay.
Is it obvious that it is a cone? Is it obvious that it is a cone?
Yes. So we need. So we will use just that. There are two components. This is two signs of x0 that we have here. So if it's +1, then this is one component. Is -1, this is this component. So geometrically, this is an interior of the corresponding one.
Yeah, and also you mean x squared larger than 0 or
0, 0, 0, 0.
And on remark property here we can, instead of K3 surface, any projective smooth surface.
But then we should consider numerical group.
Okay, yes.
Because we have this theorem of signature just for numerical classes.
Right.
And for K3 surface, we just can't pick up. Okay, so it has two components. Plus and 0 minus, and suppose that we have an element from one connected component and an element замыкания. Closure. Да, я не выспала. Вот. And an element in the closure of this component that is not 0, then in fact this intersection is greater than 0. And moreover, so there is a mess just because this is a reminder from linear algebra course. And for an element from the other component, we have negative self-intersection, and this hyperplane separates two components. So we can say that two elements lie in the same component if their intersection is positive. Okay? So, and now let us discuss what we have here. So S is a projective K3 surface. Then we will define its ample cone. Ample cone. By definition, this is positive linear combinations of ample line bundles. L R, where R is some positive number, L R are positive reals, and this are ample line bundles. So this is the ample cone. For a non-projective K3 surface, we can also define it, but it can be empty. Okay, and now let me formulate the following statement. So if S is a projective K3, then ample cone is an open convex non-empty cone. Ample line bundles, ample line bundles are points of intersection of this cone with Picard group, and ample cone lies in the connected component of the cone that we discussed before. That is elements with positive. So we have already discussed that there are two components, and we claim that ample cone lies in one of this connected component, and we will call this we will call this component positive cone of S. Positive of S. So there are two components, and we define and we will call positive cone of S the component that contains ample the ample cone of S. Okay? So now let me present the proof. So suppose choose a basis. This is Picard rank. A basis of this real vector space that consists from elements of pic S consist of or или from, ладно, не важно. Elements and suppose we have an element in ample cone, so this is a positive linear combination. Okay, then what we have? Know that there exists K big enough such that if we twist or all mi by L1 in a big enough degree, then this will be ample line bundle for all I. So if we choose, so now I'm trying to explain why this is an why it's open, why this ample cone is open. So suppose we have here positive mu, then consider the following linear combination. We can write it in the following strange way, but I will explain. S L1 plus mu I 1 plus mu I. Here I is 2s, and no. Right? We just add it here, and then we take it with minus sign here, and then add it here. Right? Right? So we just so x is this linear combination. We just added add some linear combination of our bases, and then we write it in such a fancy way, just adding this sum here and take take with minus sign this sum, and here with plus sign. Okay, so note that if sum of mu I.
Wait, why there is only L1? Because X is a linear.
No. Here we still should have just L1. We add it here and consider it minus. So here is just L1, and here is just L1, and then MI.
But then where is, for example, where is R times LR?
Just. Yes, we should add also.
So would be M.
So here, what if it, no. Сейчас. What should we add here to obtain this sum? L1,
Just like
you
that.
add?
I times
No. Here we should take definitely this one, and here we just take
I equal to 2 to R.
lambda I from I2 to R.
Yeah.
Right? Okay, yes. Now everything is okay. So suppose now that sum of this mu I is less than lambda 1 over k. Yes, so that this is something positive. Then we have x I. Yes, then this belongs to an ample cone of S. Just because these summands already are in an ample cone, this is our supposition that we take a big enough twist, right, of Li. So this is an ample line bundles with positive coefficients. And this is also an ample line bundle with positive coefficient because we take this sum in such a way. Okay? So this means that there exists a ball with center in X in this ample cone. Okay? So we fixed an element here, and we know that for such sums, this lives in an ample cone, right? So there exists a ball centered in X in ample cone of S.
So all the
Okay.
LIs are just ample line bundles.
Yes, yes. MI was just basis that induced from Picard group, but we have a third theorem that tells us that we can.
Yes, yes, yes.
So we obtain that this is something open.
But our I is positive for.
But we can consider mu I or minus mu I. Doesn't matter. So we obtain an open ball in ample cone. Okay, and for the next statement is more or less obvious because for an
No, if mu I is a negative, then the second summand will be anti-ample.
what? No. If we can consider mu mi or minus mu I, it doesn't matter.
We consider
So okay,
mi
let me
or minus mi or mu I minus mi.
We can choose another basis, just take minus mi, big mi.
Okay.
So now for an ample class H on S, and for all elements in an ample cone, of course we have Hx is positive for Hx is definitely positive just because this is ample line bundles. And this is an ample class. Okay, so we immediately obtain the second statement of our lemma, and the last thing that we need to prove is that about this intersection. Of course, all ample line bundles lives here, but we want to prove an opposite statement that if we have an element here, then L is ample, right? We want to prove that L is ample. So suppose that L is a
Don't understand with the second pickup.
Picard group of S.
An ample line bundle belongs to the pickup group automatically, or what do you mean?
No. So this is a cone over real numbers.
Ah,
So this is a cone over
Yeah.
real, yes. And there is an intersection. Of course, all ample line bundles lives in this intersection. But we want to prove the opposite statement, that if we have an element here, then this corresponds to an ample line bundle. So suppose we have,
And this is for any projective. Right. Any projective cube, not a K3 surface, right?
what exactly?
This statement.
But here I also explained that for Picard K3 surface, it's
Numerical.
numeric for all we should consider numerical classes. Only just for K3 surface we have this. Not only just, but for K3 surface we have this identification. In general, we don't have. So we have this element. Then what we know that its square is greater than 0, just because we already proved that lies in the positive cone. And in fact, its intersection with all integer curves is also positive for all curves in S, right?
Then example, yes.
Yes, then it's simple. So there is a statement that I will just formulate. That I just want to formulate. I will not even write it down. That if we have a class that with positive self-intersection in Picard group, such that its intersection with all curves is positive, then this class is ample. Okay? Okay. And now, now we proved the statement about ample cone. And now we want to understand what is the difference between these two cones that we have. Positive cone, that is a connected component that contains ample, and ample cone. So let me write down the statements that I formulated one more time. If we have a positive class that lies in the Picard group, then it's ample if and only if it has a positive intersection with all irreducible curves. For all curves on C. So this is a characterization of ample classes here. But in fact, for K3 surface, we can make more precise statement, because for K3 surface, it's enough to consider intersection with rational curves. Okay, so let me prove. So here we consider all reducible curves, and for K3 surface, it's enough to consider just rational -2 curves. So for this, let me recall that for an integer curve is an integer curve. Then from Riemann-Roch and our favorite exact sequence, we have the following equivalences. C is a smooth rational curve. So this is a consequence of Riemann-Roch, and that we tautological exact sequence, and so we have already discussed this statement. Okay. And now let me define two more subsets. So first, in Picard group, we consider classes with -2 intersection, and now we consider classes here. So we consider classes with -2 intersection in Picard group with non-zero cohomologies. So first of all, note that this set can be decomposed as the delta plus and minus delta plus. So this is more or less statement that if we have a class with -2 intersection, then it's the corresponding bundle or its dual has a global section. So let me write down. So we consider sum of S of global sections of M and M dual. Then of course this is greater or equal to M dual. And by Riemann-Roch, this is what?
Two plus the self-intersection of M over 2.
And since we have this,
This is this is 1.
okay, and so we should have global sections of M or M dual. Okay, so for so we have this decomposition. So we consider M or M dual. It has global sections, and this gives you this decomposition. Okay, and now. Yes, for example, yes, and also another comment, of course, this delta plus contains all classes of rational curves on M,
Yes.
right? But also it can consider, it can contain something more. For example, if we have C1 and C2 rational curves that transversally intersect in one point. So 1 and C2 is 1 on S. Then the class C1 plus C2 lives here. It has some non-trivial global, the corresponding line bundle has non-trivial global section, and its self-intersection is -2. So it contains all rational curves, but also can contain something more.
Yes.
But not that there are some cases when there are no rational curves on K3 surface. But in any case, we can consider this set. Okay. And what next? And how we can and of course, how we can distinguish between these two components for an ample line bundle L and M del. We have M and delta plus if and only if Lm is positive. As before, we can. So there are two components, and M is in positive component if and only if its self-intersection its intersection with an ample line bundle is positive. Okay, now let me formulate theorem. So let S be a projective K3 surface then this cone can be defined as classes in positive cones such that for all M plus xm is positive or classes such that for all rational curves its intersection with C is positive. So that's the answer. What is the difference between positive cone and ample cone for K3 surface? So we should check that the intersection with rational curves is positive. It's enough. So let me present proof. I think I have time for this. So of course we have an embedding. And this is embedding. Smooth rational. So what we want to prove is that we have, so to prove the statement, it's enough to prove that if we have such a class, then it lies in an ample cone, right? Okay. So in since this is dense in all these subsets, it's enough to show that if X lives here, is such that its intersection with all rational curves is positive, or all rational, then X lives in ample cone, right? So we consider a rational class that lives in a positive cone such that its intersection with all rational curves is positive. We want to prove that this means that it lives in ample cone. Okay, and now we can suppose that X is an integer class. So X is a line bundle. On S. So we can denote it by L is a line bundle L on S. So what we want to prove is that LC is positive for all irreducible curves. For all irreducible curves. And so there are two cases. First, if this curve have a non-negative self-intersection, then we know by definition that it lives in the closure of this positive.
L times C is positive because that's our goal.
No. We want to prove. We want to prove. We want to prove that this is positive for all curves. From this, we will obtain that this is an ample line bundle. So first, suppose that C has positive self-intersection, so that it lives by definition in this closure. But this means that since L is in the same, since L lives in positive cone, we know this, right? By our assumption. We have already proved before in our lemma that this is positive, because they live in the same component that have positive intersection.
Yes.
Okay? And now the next So we have already discussed several lectures ago that for an integer curves from Riemann-Roch, we know that this is self-intersection is greater or equal to -2, right? So, and it's always even, yes. So if it's not positive, then C, its self-intersection is -2.
Yes.
But this means that C is rational. We have already discussed this. Smooth rational. So we have this by assumption, because we assumed that this have positive self-intersection with all rational curves. Okay? Okay. So we have proved that for K3 surfaces to check that something live in ample cone is something easier, because it just we can just consider its intersection with rational curves. It's enough. Okay. So if there are no rational curves, we have no problem. And now let me also say something about Keller cone. Because, as I already mentioned, general K3 surface is not projective, it's just Keller. So our ample cone for a general K3 surface is just empty. And its analogous is, in general case, it's Keller cone. So we can define for any complex surface its Keller cone K it's Keller cone, and this is in fact an open convex cone of all Keller classes that lives in 1-1 part. Right? So we can just consider the cone that corresponds to Keller classes. And this is open convex cone. We can always define it. Okay. So Kx is a subset of a real vector space and it also contains in a connected we still have this so we still have H11 XR with we still have two connected components of this cone, right? And in fact, Keller cone will live in one connected component of this thing. Lives in a connected component of this cone, and this connected component is called a positive cone. Positive cone of X. So just as we have, the picture is resembles an algebraic case. And let me also give a comment that what is, of course, ample cone, if it's non-empty, it is contained in Keller in a Keller cone of X. And this is in fact rational points of this scalar cone, because there is a we discussed last time that there is a Kadeira theorem that tells you that if you have a rational Keller class, then it gives you an embedding of the corresponding surface to a projective space. So this is a subcone generated by integer points. Of Keller cone. So integer points of Keller cone generates your ample cone. But there are some cases when there are no integer points. In general, there are no integer points in for a Keller cone of a K3 surface. Okay? But so that's why this definition of positive cone is coincide with the definitions that we have before. Because if we have ample line bundles, if this corresponding cone is non-empty, then it's contained in Kx. So we can consider the corresponding connected component of this cone, right? And this is a positive cone, as before, okay? But the problem is that sometimes this is, for a general K3 surface, this is empty, and in fact, these are just integer points of Keller cone. And okay, is this clear? So I tried to explain the whole picture with the ample line bundles just because it's easier to understand what we have for ample line bundles before we work with Keller class. Okay, and now let me formulate the statement of Torelli theorem in the whole generality. So, as I said before, S and S prime are isomorphic if and only if there exists an isomorphism phi between the corresponding Hodge structures. And now, I explained all this just to formulate this moreover. Moreover, there exists an isomorphism between S and S prime such that phi is induced from this isomorphism if and only if complexification of the corresponding map of Hodge structures maps Keller cone. Note that Keller cone of S is always non-empty, right? Even for non-projective one, we have all K3 surfaces are Keller. So this Keller cone is non-empty. So we can consider Keller cone here. We can consider where it is mapped by this isomorphism, and we claim that the corresponding morphism induced from the morphism of corresponding K3 surface if the image intersects Keller cone of S prime in a non-empty way. Okay? This is the whole statement.
Кто-то из них в другую сторону должен быть, да?
Что?
Кто-то из них должен быть в другую сторону, да?
Почему? Какая разница, все равно изоморфизм?